Dark matter is a mysterious and elusive substance that pervades the universe, exerting gravitational influence on galaxies, stars, and cosmic structures. Despite its invisibility and enigmatic nature, dark matter plays a crucial role in shaping the cosmos as we know it. In this extensive exploration, we'll delve into what dark matter is, how it was discovered, its properties, distribution, and the ongoing quest to unravel its secrets. Discovery of dark matter. The story of dark matter begins with observations of the motions of galaxies in the 20th century. Astronomers found that the visible matter in galaxies, such as stars, gas, and dust, could not account for the observed gravitational forces that held these galaxies together. Instead, there appeared to be additional unseen mass providing the gravitational glue necessary to explain galactic dynamics. The term dark matter was coined in the 1930s by Swiss astronomer Fritz Zwicky, who studied the Coma cluster of galaxies and found discrepancies between the observed mass and the mass calculated from the galaxy's motions. Zwicky proposed the existence of unseen Dunkel Materie, dark matter, to explain this anomaly. Decades later, in the 1970s and 1980s, further evidence for dark matter emerged from studies of galaxy rotation curves and the dynamics of galaxy clusters. Observations indicated that the visible matter alone could not account for the observed velocities of stars and galaxies within these systems, leading astronomers to conclude that there must be significant amounts of unseen mass contributing to the gravitational potential. What is dark matter? Dark matter is a form of matter that does not emit, absorb, or reflect electromagnetic radiation, making it invisible to telescopes and other instruments that detect light. Unlike ordinary matter, which consists of atoms and subatomic particles such as protons, neutrons, and electrons, dark matter is composed of as yet undiscovered particles that interact weakly with ordinary matter and radiation. The nature of dark matter particles remains one of the central mysteries in modern physics. Various theoretical models have been proposed to explain dark matter, ranging from hypothetical particles such as weakly interacting massive particles, WIMPs, and axions, to more exotic possibilities such as primordial black holes and sterile neutrinos. Properties of dark matter. Despite its elusive nature, astronomers and physicists have inferred several properties of dark matter based on observational data and theoretical models. Non-luminous. Dark matter does not emit, absorb, or reflect electromagnetic radiation, so it cannot be directly observed with telescopes that detect light. Instead, its presence is inferred from its gravitational effects on visible matter and light. Transparent. Dark matter does not interact electromagnetically, so it does not emit or absorb light. This property allows light from distant objects to pass through dark matter unimpeded, making it difficult to detect directly. Cold. Dark matter particles are believed to be cold, meaning they move relatively slowly compared to the speed of light. This property has important implications for the formation and evolution of cosmic structures, such as galaxies and galaxy clusters. Clumpy. Dark matter is thought to be distributed unevenly throughout the universe, forming clumps and filaments known as the cosmic web. These structures serve as the scaffolding upon which galaxies and galaxy clusters form. Weakly interacting. Dark matter interacts with ordinary matter and radiation primarily through gravity and the weak nuclear force, making it difficult to detect using traditional experimental techniques. Evidence for dark matter. Several lines of observational evidence support the existence of dark matter. Galaxy rotation curves. Measurements of the rotation curves of galaxies indicate that stars and gas in the outer regions of galaxies orbit at higher velocities than would be expected based on the visible mass alone. This discrepancy suggests the presence of additional unseen mass, presumably dark matter. Gravitational lensing. The bending of light by massive objects, known as gravitational lensing, provides indirect evidence for the presence of dark matter. The gravitational influence of dark matter can distort the images of distant galaxies and produce multiple or distorted images of background objects. Cosmic microwave background, CMB. Measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, provide constraints on the composition and distribution of matter in the early universe. The observed patterns in the CMB are consistent with the presence of dark matter. Galaxy clusters. The dynamics of galaxy clusters, the largest gravitationally bound structures in the universe, provide further evidence for dark matter. Observations of galaxy clusters reveal that their mass distributions far exceed what can be accounted for by the visible matter alone, indicating the presence of significant amounts of dark matter. Distribution of dark matter. Dark matter is believed to be distributed throughout the universe in a vast cosmic web of filaments, sheets, and voids. This cosmic web structure emerges from the gravitational interactions of dark matter particles over cosmic time and serves as the framework for the formation and evolution of galaxies and galaxy clusters. On small scales, dark matter forms dense halos around galaxies, providing the gravitational seeds for the formation of stars and planetary systems. These dark matter halos extend far beyond the visible boundaries of galaxies and contain the majority of a galaxy's mass. On larger scales, dark matter filaments connect galaxy clusters, creating a cosmic web that spans the universe. These filaments funnel gas and galaxies along their lengths, shaping the large-scale structure of the cosmos. The role of dark matter in cosmology. Dark matter plays a central role in the standard cosmological model, known as the lambda cold dark matter, lambda CDM model, which describes the evolution of the universe from its earliest moments to the present day. In the lambda CDM model, dark matter serves as the gravitational scaffolding upon which galaxies and galaxy clusters form, providing the mass necessary to overcome the universe's expansion and facilitate the growth of cosmic structures. Dark matter also plays a crucial role in the formation of large-scale structures such as galaxy clusters and superclusters. The gravitational attraction of dark matter causes overdensities in the cosmic web to collapse and merge over cosmic time, leading to the formation of increasingly massive structures. Challenges and unsolved questions. Despite the wealth of evidence supporting the existence of dark matter, many questions remain unanswered. Nature of dark matter. What is the true nature of dark matter particles? Do they belong to one of the known particle species in the standard model of particle physics? Or do they represent new physics beyond the standard model? Detection methods. How can we directly detect and study dark matter particles in the laboratory or through astronomical observations? What experimental techniques and instruments are needed to detect the elusive signals of dark matter interactions? Cosmic coincidence problem. Why does the density of dark matter in the universe appear to be roughly equal to the critical density required for a flat universe, leading to the so-called cosmic coincidence problem? Modified gravity theories. Could the observed gravitational effects attributed to dark matter be explained by modifications to the laws of gravity on large scales, rather than the presence of unseen matter? Galactic dynamics. What is the exact distribution of dark matter within galaxies, and how does it influence the formation and evolution of stars and planetary systems? Conclusion. Dark matter stands as one of the greatest mysteries in modern astrophysics and cosmology, challenging our understanding of the fundamental nature of the universe. From its discovery through its role in shaping the cosmos, dark matter continues to captivate the imagination of scientists and researchers around the world. While much progress has been made in elucidating the properties and distribution of dark matter, many questions remain unanswered. Future observations, experiments, and theoretical developments promise to shed further light on this enigmatic substance, potentially revolutionizing our understanding of the universe and our place within it. As we continue to explore the frontiers of astrophysics and particle physics, dark matter stands as a testament to the enduring mysteries of the cosmos and the relentless pursuit of knowledge. Thank you for watching. Please subscribe our channel.